All right, so this is going to be our kind of lab demonstration video for Lab 11 for our 1211 labs. This is our experiment where it's not so much a wet lab experiment, but really more of a look into Lewis structures and covalent bonding, as well as looking at VSEPR geometries. And for this demonstration, I'm mainly going to be working through examples. If you're looking for like the exact steps on how to outline and draw Lewis structures, as well as like how to find these VSEPR geometries and kind of the tables for doing that, we do have our pre-lab video up that has pretty much all of that walkthrough and kind of introductory information. This demonstration is more just going through like the actual examples. And so I'm going to go through a handful of examples, demonstrating most of the things that are talked about in the pre-lab video, as well as kind of the lab reading, because really Lewis structures are one of the most important things you guys see in all of 1211. And so we really want to make sure that there's kind of some time spent and hopefully enough examples here that we'll walk through, that you kind of understand what's going on with them. You get comfortable drawing Lewis structures, identifying kind of geometric shapes, because that's something that is very critical, not just to 1211, but to future chemistry courses. For instance, like the first couple weeks of 1212, if you're not comfortable drawing Lewis structures or identifying shapes, it's going to make it very difficult to then expand onto intermolecular forces and polarity and some of the other things that are going to come out of this. So what I want to do is just kind of jump into actually taking a look at some examples of different things that are in the packet. So I'm going to take a look at a few examples of molecules that are in the packet and a couple examples that aren't, just to kind of detail some different things that you're going to be expected to do. And hopefully, like I said, mainly just go through the steps so that everyone's kind of comfortable with what they're going to be doing. So as a starting point, what I'm going to do is actually just pick a molecule. And so what I'm going to pick is the first molecule that we take a look at. I'm going to choose PCl3. And I'm going to make one note in here. If you're looking in your labs, we caught this kind of late. It was like a last second change, I think, that happened that we didn't quite catch when it happened. But in your labs, your second example, I think, says POCl3. You can go ahead and cross that out and do PCl3 instead. And so a couple, like I said, these first couple examples are ones from your packet for CSE Pub. And like I said, I'm just going to kind of walk through everything so that you see all the details and pieces that you're going to need. So for PCl3, if the first step that we want to actually kind of go through is drawing out a full Lewis structure, what we want to be able to do is identify how many valence electrons we're going to be having to work with. Right? It's usually kind of the first two steps that you always try to identify is how many electrons are you going to have in your structure, as well as what's the general skeletal structure. I usually find the electrons first and then do a skeletal structure. The order for that exact step, not necessarily important, but at some point, the number of valence electrons we have to work with is going to matter. So for finding valence electrons, I'm going to jump to a periodic table here for us to look at. So if we're looking at PCl3, we're going to first find phosphorus on the periodic table. So here we have phosphorus. And if we're finding valence electrons, remember, we're basically just counting our way across, right? So 1, 2, we skip all of this D block for all of our covalent nonmetals over here. And so then we have 3, 4, 5 for nitrogen and everything below it, which includes phosphorus. So phosphorus should have 5 valence electrons. And then we also have chlorine was our other molecule, which is right here. And so if this was 5, then 6, 7 for all of our halogens. So each chlorine is going to have 7. So that means if I jump back to our page here, if I have phosphorus, it's going to have 5 plus 3 times 7 electrons for each of the chlorines. That means I have a total of 26 electrons. Right? That's the number of electrons I'm going to have to be able to draw my structure. Now, to start putting this structure together, the skeletal structure is always going to start with a central atom. And for almost every example that we really see in general chemistry, whatever our first element is that we're given in a formula, that's probably going to be your central atom unless that first element is hydrogen. That's probably a good general rule of thumb that you'll normally see. For the most part, at least for 1211, if we give you a structure, assume there's always one central atom with kind of everything attached to it, unless we tell you otherwise. We're not really going to get into any things with like chain-like structures just yet. We'll work our way to that kind of with 1212 and organic and other classes. For right now, the kind of just real fundamental basics, expect there to be one central atom, usually the first element listed, with kind of everything attached to that. So for attaching everything, we're always going to initially just attach everything with single bonds. So we have 3 chlorines. I'm going to just kind of space them out a little bit here. And we'll worry about the 3-dimensional shape in a moment. And so for this part now, we're done with the skeletal structure. We have our total number of electrons we're going to have to work with. The next step in our process was filling the outer or the terminal octets. So adding lone pairs to all of our outer atoms, which basically means adding 3 lone pairs to each of them to go with the 1 bond they each have will give them their octets. And now I've filled all those outer octets. But what I want to do is actually go through and count how many total electrons have been used here, right? And I really have, here's 2, 4, 6, 8, because each bond is 2 electrons. There's another 2, 4, 6, 8, another 2, 4, 6, 8. So basically I have 3 octets that I've now drawn. So 3 times 8 should be 24 electrons that I've used. And if I've used 24 electrons, that means I should still have 2 electrons left over. And so anytime there's leftover electrons, they will always be a lone pair on the central atom. There are no exceptions to that. Your extra electrons will never make multiple bonds, which I think is a very common mistake that I see a lot of people make kind of early on as they're learning how to draw Lewis structures. Those extra electrons, always going to be a lone pair. Now, when we're looking at this molecule, we're not quite done in terms of like our normal Lewis structure steps. Usually what we'll look for once we've added a lone, like any leftover electrons as those lone pairs, we check to make sure the central atom has at least an octet. So if we look at that phosphorus, in this case, it has 3 bonds on it, and it also has a lone pair. And so between the 3 bonds, which have 2 electrons each, and then the 2 electrons in a lone pair, phosphorus has 8 electrons around it, which satisfies then its octet rule. It has its 8 electrons, it's happy, we don't have to make any multiple bonds in this case. And the very last thing I would suggest everyone always check when you get to this point is just look for what we call formal charge, right? And one of the things we said before, if you go through kind of the videos, or formal charge, which I'll abbreviate here, right, it's typically our number of valence electrons, and we do this for each individual atom, minus your number of bonds that atom is making, minus the number of electrons in lone pairs. And so I'm doing some abbreviations here, but that's kind of the general way we normally find our formal charge. And so if I want to look at, for instance, the chlorine atoms in this structure, the nice thing about formal charge, it's really, really pattern heavy. All of those chlorines have 3 lone pairs and 1 bond, so all of them should have the same formal charge. And if I was going through that for chlorine, they have 7 valence electrons, they each have 1 bond, and they each have 6 total electrons in the 3 lone pairs that each of them have. And so 7 minus 1 minus 6 is 0. And really that's what we want to see. We want to see 0 formal charge for as many atoms as possible. That's how we get the best Lewis structures. And in this case, all the chlorine should have a 0 formal charge. We can do the same thing for the phosphorus. And what we see for phosphorus, it would normally have 5 valence electrons. It's got 3 bonds. And then we're subtracting 2 electrons in the 1 lone pair that it has. It also has a 0 formal charge. And if things have a 0 formal charge, you don't have to write them in anywhere in the molecule or in your Lewis structure. You can just kind of leave them as they are. And like I said, that's a good thing. That's what we usually like to see when we're checking for those formal charges. So that means that what I have drawn here, this would be our final Lewis structure. But there's some other pieces that this lab wants you to take a look at. Right? This lab is also going to be taking a look at having you identify what it calls an electron geometry. As well as a molecular geometry. I'm going to abbreviate slightly here. And these are really where you're going to figure out the real shape information for your compound or for your molecule. So your electron geometry. When we're looking for our electron geometries, remember we're always looking for how many total things are around the central atom. So in this case, we have 3 attached atoms to the central atom, and we have a lone pair, which is 4 total things. So if we have 4 things around the central atom, our electron geometry is always tetrahedral. Right? That's the normal pattern that we see. If we had 2 things around the central atom, it'd be linear, 3 the trigonal planar, 4 tetrahedral. If we go beyond 4, we can get to trigonal bipyramidal for 5 and octahedral for 6. For the molecular geometry now, this is the part where it gets a little bit more complicated because the molecular geometry always is going to start from the electron geometry and then really look at the lone pair situation on your central atom. Because the reality is, even though I've drawn this molecule like this, where everything's looking like it's kind of in this trigonal flat shape for all the atoms, that's not the actual arrangement of those atoms in 3 dimensions. Right? If that molecule is going to properly spread out, if it's got a tetrahedral shape around the central atom, That means the shape of the atoms themselves, which is really what the molecular geometry is trying to look at. In this case, if we start from tetrahedral and we have one lone pair and 3 bonds for the central atom, or 3 bound atoms, what we're going to end up seeing then for our molecular geometry is what we call trigonal pyramidal. And that means that this thing's going to look kind of like a pyramid in 3 dimensions. And I can show that on paper, even though like a pyramid's a 3-dimensional shape, I can show that in 2D on a page. And so I'm going to show that a little bit of what's called, and this is what we call then our Vesper sketch. So when you're in your CSE Pub packets, kind of filling out your different boxes, if we want to look at the Vesper sketch, so I'll label this as the Lewis structure over here. And admittedly, some people like you to draw the Lewis structures in the correct shapes that you have for your Vesper drawings. Personally, I don't usually care that much, but if you're familiar with Lewis structures enough, that is something I would eventually try to do. I think it usually makes things look a little bit better. But in this case, the way we would normally draw a Vesper sketch for something with a tetrahedral geometry, and really just that's, I think, the most effective way to draw this VSEPR sketches, is just figure out what is your structure like starting out for your electron geometry, draw what that looks like first, and then just add all of your pieces. So for this one, if we're starting out with something that's tetrahedral, we're going to take a phosphorus atom, and a tetrahedral arrangement, we can always draw something like this, right? Where we have 2 lines that are actual lines, then we have kind of I'll make this wedge a little more pronounced, basically a wedged and a dashed line. When we see those wedges, these wedges basically mean we have something coming out towards us. The dashed lines mean we have things going back away from us instead. And now for putting our pieces on, the nice thing for tetrahedral geometries like this, it doesn't matter what goes where. All of these positions are equal to each other. For instance, if I spin this thing around basically in axes here, these can all switch places and you can kind of rotate them around. So it doesn't matter where we put kind of our different atoms in this case. So for us, we have one lone pair. If we want to put the lone pair on top, we can put the lone pair on top. I think that's maybe the best way to look at this, because then that lets you see that trigonal pyramidal molecular geometry a little bit better. And then we can put our chlorines on the bottom, right? And that can be our Vesper sketch. Like the lone pairs in the outer atoms isn't really important here for the Vesper sketch. The lone pairs in the outer atoms will matter more next week when we start talking about something called valence bond theory. But for right now, for a Vesper sketch, outer atoms, lone pairs, not really important. All we're really looking at is trying to really show and identify these geometries that we're describing. So electron geometry is tetrahedral. So that's why we have this kind of starting arrangement around the phosphorus. And then to show that it's trigonal pyramidal, I put the lone pair on top, and now here's your trigonal pyramidal shape, right? We have a pyramid where the phosphorus is the point, and we have a triangular base to the pyramid of our 3 chlorines. So that would be kind of our outline kind of for our process of going through kind of our different pieces of things that you're going to be asked for in the lab itself. So I think it usually asks for, like, if you go to your CSE Pub packets, it's going to be asking you for things like, the number of electrons you have for your structure. It's going to ask you to draw the Lewis structure. It's going to ask you for those different geometries, the electron molecular geometry. And then it's also going to ask for a Vesper sketch. So we want to get comfortable kind of doing all of those things. And I think the best way to do that is, again, just doing a few more examples. And so I want to show some additional examples so that everyone can kind of see kind of the whole process being done with this. And so the next one I'll take a look at doing, I believe this one's not in the packet, but I will do 1 or 2 more from the packet itself. So let's take a look at carbon dioxide, CO2. It's a pretty common molecule. You may have seen kind of some of this process done for it in the past, but I think this will hopefully, again, illustrate some different things that'll be useful for us. So for CO2, if we're going to go through kind of all those same steps that we saw before, we want to know how many valence electrons we have to work with. So I'm going to bounce back to a periodic table here real quick. And if I look at a periodic table, I'm going to notice here I have carbon. So for carbon, 1, 2, 3, 4 for its valence electrons. And then for oxygen, if carbon was 4, we'd have 5, 6. So oxygen has 6 each. So the 2 oxygens having 6, the 1 carbon having 4. Adding those together, 4 plus 2 times 6. Should be 16 electrons, right, that we should have to work with in our structure. And for our general skeletal structure, we can start with a carbon and those 2 oxygens attached to it, with just single bonds always to start. Now, The next piece of this is going to be that we want to go ahead and add kind of our lone pairs and things like that to our outer atoms. So lone pairs to the outer atoms. And then anything that's left over, we put on the central atom as a lone pair. So when we look at what we had 16 electrons, but if we count the electrons that we've used, we've actually already used 2, 4, 6, 8, 10, 12, 14, 16. We've already used all 16. But the problem is, if we look at our central carbon here, we don't have an octet yet. In fact, we only have 4 electrons. So this is the instance where we make double bonds, right? We need multiple bonds. So we can take a lone pair off one of the outer atoms and add it to the central atom. So I'm going to erase these 2 lone pairs and then add an additional bond. That gets us to 6 electrons on the carbon. But then I need to do the same thing on, I'm going to do it on the other oxygen, but I'll explain why in a second. But I need to make a second multiple bond in order to actually get that octet on carbon. Now, one thing that you might be asking right now is like, why did I choose 2 double bonds and why didn't I do this instead? And this actually goes back to the formal charge that we talked about in our first example, right? So if I wanted to calculate formal charge for things, for this top structure, if I'm looking at the top structure, the formal charge of every element in the structure actually ends up being 0. But if I look at this structure, my 2 oxygens don't look the same, which means one of them has to have a formal charge. Like that's the only, if they don't look identical, one of them will have to have a formal charge. And it turns out they actually both have a formal charge. The one with the single bond has a -1 formal charge, so the triple bond would have a positive. And since this has non-zero formal charges and this one doesn't, the top one is the better structure. So if we were giving just the Lewis structure for CO2, that's what we're asked for. Like what we want to actually draw is actually just going to be that top structure. Just the top one's going to be our better Lewis structure. Now, for the other things that we're often asked, like I said before, like in our previous example up here, we also looked at geometry in the Vesper sketch. So for electron geometry. So electron geometry is mainly based on how many things are around that central atom. Well, in this case, if we're looking at that carbon, it's not about the bonds, it's about how many things are attached. And there's only 2 things attached to the carbon. So for our electron geometry, anytime there's only 2 things attached, the electron geometry is linear. And the nice thing about a linear electron geometry, it also means that our molecular geometry will also be linear. All right, last bit of this one, Vesper sketch. Vesper sketches are actually really easy for things that aren't 3-dimensional, right? A linear geometry is really easy because we have a carbon and our 2 oxygens, right? If you want to put double bonds, you can, but the reality is we're just trying to show things in 3 dimensions. And if we're showing things in 3 dimensions, this thing's flat. So we don't have to use any fancy wedges or dashes. Again, we don't care about the outer lone pairs. We don't even really care about single versus double bonds. The Vesper sketch just shows the 3-dimensional orientation, which everything in this is just a straight line, and that's all we would want. So that should be everything then for our carbon dioxide example, if we were going through all the pieces for it. Now, a couple more examples. Like I said, I'm going to do probably just 2 more here and hopefully kind of wrap up so we can kind of see all the main features I think that we want to see for things. All right, so for the next example, we're going to take a look at nitrate. And so when we're looking at doing, sorry about this on our screen there. If we're taking a look at nitrate, 3-. This has a couple different things going on in it than what we've seen in some of our previous examples. So first, we'll still start kind of the same normal way we've been looking at things. So we'll take a look at periodic table, find nitrogen on our periodic table. So if we go to look for nitrogen, see it here, counting over 1, 2, 3, 4, 5. Right, it's above phosphorus that we saw before that had 5. So nitrogen has 5 valence electrons. Oxygen's 1 more spot over, so each of them will have 6. And the thing that's different this time is we also have that negative charge. So if we have that negative charge, that means we have 1 additional electron beyond what kind of our normal count. So that means we're going to have our 5 electrons from the nitrogen. We're going to have 3 times 6 electrons each for the oxygens. And we're just adding 1 for that negative charge. So that's going to give us a total of 24 electrons. All right, so we have 24 electrons to get our structure started. Again, steps we're going through the structure, still the same general steps, still very systematic. So skeletal structure, Nitrogen is the first element in the formula. Should be the first atom, or it's going to be our central atom then for the structure. You have 3 oxygens around it. And then we're going to fill all those outer octets. So 3 lone pairs on each of those oxygens. And that's going to leave us now with, if we go, well, now we have to go back and kind of count and see what electrons we might have left over to put on the central nitrogen. So we started out with 24 electrons. So now if we go through and count everything, notice we have 2, 4, 6, 8, 10, 12, 14, 16, 18, but then I have the 3 bonds that I've skipped, right? It should be 20, 22, and 24. So we do have 24 electrons that we've already used. So that means we don't have any electrons left to put on the nitrogen as a lone pair. But again, the problem here, kind of like we saw with CO2, that nitrogen doesn't have a full octet yet. So how do we fix that? Well, we need to make a multiple bond. In the previous example, we saw we actually had to make 2 multiple bonds. In this case, though, we should really only need 1. So to do that, I'm going to choose just the top oxygen for now, as far as where to make that second bond. So I'm going to take a lone pair off that top oxygen, add a second bond. And now, when I'm looking at this, I have the octet on my nitrogen, but I also have kind of a question to ask myself. How did I know to make the multiple bond to this top oxygen versus one of these other ones? And the real answer is you don't. You actually end up with something else that's called resonance. And so what resonance means is that we actually have different ways of drawing the structure that are pretty much identical to each other in terms of how stable they're going to be. So let me clean this up a little bit as I draw this. So I could have also drawn the double bond to the lower left oxygen, or I could have drawn the double bond to the lower right oxygen. Right? Could have done it to any of them. And in terms of what's better, none of them are better than the other. They're all pretty much the same, right? And how we know that these things are equal really to each other is through, again, formal charge. And remember before I said formal charge is very pattern-based. So for instance, when we're looking at these oxygens that have double bonds, remember when we saw oxygens in that last example of CO2, an oxygen with a double bond and 2 lone pairs? Even though it's a different molecule, it's still the same kind of setup around the oxygen. Oxygens with 2 bonds and 2 lone pairs have 0 formal charge. Oxygens with 1 bond and 3 lone pairs have a -1 formal charge. So each of these will have a negative formal charge. If I look at my other structures, I'm again going to have 2 negative formal charges on oxygens and 1 0. Same thing on the bottom one, I'd have 2 negative formal charges and 1 0. And the nitrogen in all of these looks the same. It has 4 bonds in each of them, which actually means nitrogen is going to have a +1 formal charge on all of these. And so all of them have the same kind of distribution of formal charge, and that's really how we tell what structures are better. And if they're all the same, then they're all equal in terms of how, which one is better. So this is what it really means to have what we call this resonance. We have a couple of different ways to draw the same structure that are all equivalent to each other with none of them being better. So notation-wise, a couple last things to kind of clean up this drawing. I mentioned that there's negative formal charges on the oxygens, the single bonds, positive formal charge on the nitrogen in the middle. And since this whole thing is an ion, it's the first time we've seen this, something else to keep in mind with ions, we always put the whole structure in brackets, usually with the charge on the outside. That's what's representing this whole thing is an ion. And one of the things you'll note is that this charge on the outside, the total charge of your whole polyatomic ion, should equal the sum of all of your formal charges inside the molecule. So if the total charge is -1, notice I have a -1, a -1, but also then a +1. So altogether, these make up that -1 that we see for our charge. So we should always see that kind of work for any structure that we draw. Most of the structures that we draw, the total charge is 0, and usually all the formal charges are also 0, and that makes that a little bit easier. But anytime we do have polyatomic ions, there will be formal charges somewhere in the structure. It might only be a single one, but there is going to be a formal charge at least somewhere for anything that is an ion. All right, now, in terms of showing resonance, this will vary, like lecture-wise, will probably vary from professor to professor, but I think the vast majority of us, like here, for one structure, I've labeled everything. I have all the formal charges. I have the brackets and total charge and all of that on this structure. I don't think that's necessary to put on all of your other resonance forms. As long as you can show your double bonds kind of moving to the appropriate other location possibilities, I think that's all that really you need to detail in your other resonance forms. So don't feel like you need to draw every bit of detail for each part of the resonance structure. Put all of the detail onto one of the resonance structures, and then just indicate what those other resonance structures look like, and that should be sufficient for what we would look for grading on CSE Pod. All right, so that's everything for the Lewis structure part of this. So now the next part is kind of the geometry aspect of things. So I'm going to scroll this down. I'm going to leave just kind of the one version up there. And so if I'm going to find the electron geometry, I need to figure out how many things are around the central atom. So if I look at my nitrogen, I have 3 bound atoms. And again, number of bonds doesn't matter. I just have 3 attached atoms. There's no lone pairs, so there's 3 things. Anytime there's 3 things around your central atom, your electron geometry is trigonal planar. Right? And that means that that structure is flat. It doesn't have anything else crazy going on 3-dimensionally. So that's our electron geometry. Now, molecular geometry. Another pattern that we will often see, if you look at your central atom, in this case our nitrogen, anytime the central atom doesn't have any lone pairs, the electron and molecular geometries are going to be the same thing. Like they're just going to be the same. So our molecular geometry here, since the nitrogen has no lone pairs, is also trigonal planar. And that's because the shape of the atoms, oops, sorry about that, I'm getting tilted. The shape of the atoms that you see there, they are in that trigonal planar geometry. There's nothing kind of out of the ordinary there in terms of the molecule as a whole for where the atoms are being kind of in a different arrangement than where all your what we often call electron groups are that make the electron geometry. So electron molecular geometry the same, nothing too out of the ordinary, which means the Vesper sketch, if this thing is trigonal planar, which means it's flat, the Vesper sketch is really easy again. Similar to the last example. There's no 3-dimensional aspect to things here. So our Vesper sketch is just simply going to be showing our atoms in a apologize for my lack of artistic skill, which I have normally, and then trying to do this on an iPad is sometimes even more challenging. So Vesper sketch, just showing the 3-dimensional orientation of this in a trigonal planar shape. It's really all you would need. Again, if you want to add the double bonds and things like that, the lone pairs and the outer atoms, you can. For a Vesper sketch, I don't think that's necessary, simply because all we really want to see is that 3-dimensional shape. All right, so let's take a look at doing probably, I mentioned doing 2 more examples after the last one, but I think I might do 2 more just so we can see all the Vesper geometry shapes. So we'll take a look at 2 more quick ones, I think. And these should be also, I think, from your packet. So the next one we'll take a look at I3-. So triiodide. So this is another example of one that is in your packet, but it's also going to give us a different kind of electron geometry and Vesper sketch shape to look at, and it's a geometry that we really actually have to talk about so we can understand what the shape will look like and know why it's going to look the way it looks. So first off, drawing the Lewis structure. For I3-, if we look at periodic table, right, periodic table, we're going to look for iodine. Iodine's way down here, element 53, but it's one of our halogens. Right, we've seen halogens already a couple times. They have 7 valence electrons each. So that means each iodine has 7. We got 3 of them. That's 21 plus 1 for the negative charge. So we'll have 22 electrons for our sketch, or for our Lewis structure. So going to put things together, they're all iodines. So we're just going to pick one iodine and put it in the middle, and then make single bonds to our other 2. There's our skeletal structure. We'll fill our terminal octets as we continue to just follow our same steps as before. And now what we want to do again is figure out how many electrons do we have left that haven't been used. Well, currently in our sketch we have 8 electrons for this iodine, 8 more for this one, that's 16. We started with 22, that means there's 6 electrons left. But remember, leftover electrons, there's no exceptions, they will always be lone pairs on the central atom. So that means the lone pairs here, we're going to get 3 of them around our central atom, which seems like a lot and seems excessive because our iodine actually now has more than 8 electrons for the central atom, but that's okay. That's kind of our normal convention, and we're going to see in a second that's totally fine, right? So last couple things about this structure. Iodine does have at least an octet. It's actually over it. And remember, one of the things we do always check just to make sure, if we're going to have an expanded octet, the usual requirement is for the element to be in the 3rd row on the periodic table or lower. Iodine easily meets that requirement. It's down in our 5th row. It can take on that expanded octet, no problems. So iodine, totally fine taking on more than 8 electrons as the central atom here. But remember, we had I3 minus, so we do have a negative charge overall on this thing, which means we are going to have brackets. And if we have an overall negative charge, there's also a negative formal charge somewhere. And so if there's only one negative formal charge and there's 3 atoms here, and they're all the same element, it's really just whichever one looks different, right? Our 2 outer iodines each have 3 lone pairs, right? 3 lone pairs and a bond. And so that would be 7 minus 6 minus 1, or 0 for the formal charge in the outer iodines. But the central one, we'd have 2 electrons from this bond, 2 more from here, and then we have, formal charge. So 7 valence electrons minus 2 bonds minus 6 electrons in lone pairs is the negative 1. So the central atom here, the central iodine, does have the negative formal charge. So we can give it the little negative symbol with the circle around it for the negative formal charge. So that would be then our full Lewis structure for that molecule. All right, now, next piece, geometries for this thing. So this one, if we're looking for our electron geometry, we want to count how many things are around the central iodine. And if we count, we have 2 bound atoms and 3 lone pairs, which is a total of 5 things around the iodine. And whenever there's 5 things around an atom, its Vesper geometry for the electron geometry is trigonal bipyramidal, which sometimes you might see this abbreviated as TBP. That's kind of a common abbreviation some people will often use for that. Now, the molecular geometry is where things get a little different here. So remember when we talked about kind of adding lone pairs, or if you have lone pairs, for like the Vesper sketches in particular, for like tetrahedral, it didn't matter where things went because all the positions were the same. Trigonal bipyramidal is the one geometry that's not necessarily true. And in fact, it's actually really important to think about where those lone pairs are going to go. And so I'm actually going to draw the Vesper sketch first, and then I'll outline, kind of name that molecular geometry, because I think that will make maybe a little more sense. And so for my Vesper sketch, if I go to draw this, what I'm going to draw is I'm going to have for anything that's trigonal bipyramidal, the usual setup and orientation I will draw for it is going to look like this. And so here is how the 5 things would be arranged around the central iodine. And in this case, I have 3 lone pairs and 2 bound atoms. So I have to think about what goes where. And the general rule that we talked about kind of in the pre-lab video, you'll see it in the reading, you'll talk about it in some of your lecture classes as well. The lone pairs for this geometry always go in kind of really what I call this triangle, almost like trigonal planar part to the molecule, which are typically referred to as the equatorial positions. So lone pairs are always going to go in those spots. Doesn't matter how many lone pairs you have, they always go there. You will never see a lone pairs in the part that goes up and down of this geometry. And if you're thinking, like, what does this really look like? This is really, it's like a trigonal planar part that's perpendicular to a linear part. That's how I often think about this structure. And so for us, then, the atoms now go in these up and down part that we refer to as the axial locations for this geometry. And that would be then our Vesper sketch. And if we want to describe now the shape of these atoms, now that we understand where the lone pairs had to go, now we can talk about how the orientation of the atoms looks. Well, it looks like it's just linear. And so that's what our molecular geometry is in this case. Our molecular geometry in this case would be linear. All right. And that should cover, again, all the pieces there for our triiodide, the I3 minus. And so we have one more example I'm going to take a look at. And we'll use this one then to wrap up. So this last one that we'll take a look at, again, I want to hit kind of our last VSEPR geometry that we haven't really seen yet. And so let's take a look at doing SF6. So SF6, same steps as things that we've been doing. So in terms of valence electrons, find the periodic table. See sulfur, it's right below oxygen in the periodic table. So that means, like oxygen in the examples we saw before where it has six valence electrons, sulfur also has 6 valence electrons. And then our other element was the fluorine. And so here's fluorine. It's one of our halogens. All of those should have 7 valence electrons. So we'd have 6 plus 6 times 7, which 6 times 7 is 42, plus the 6, 48 valence electrons to work with, which is a lot. In our skeletal structure, sulfur is the first atom listed. So sulfur is going to be our central atom. We're going to attach basically all of our fluorines to it to start. And so I'm going to sketch it like this. And if you've taken enough math and looked at like kind of three-dimensional Cartesian coordinate systems recently, you're going to notice the shape looks very similar to that. And that's actually kind of the general orientation I typically draw this in. And now if I want to add, back to the Lewis structure part of this, adding my lone pairs to the outer atoms, right? That's a lot of lone pairs that I'm going to have to add. And when I'm done with this, instead of having to go back and count every single dot and every single electron, kind of the shortcut way to help you count electrons that you've used in your structure to know if there's any left over that go in the central atom, is just count how many outer atoms you have, right? We have 6 total outer atoms. Each of them have 8 different electrons around them. So 6 times 8 is 48. Well, we started with 48 electrons, so that means we've used all of them. So there's no lone pairs left to go in the central atom. That's fine, because if we look at our sulfur central atom already has 6 things bound to it, and each bond has 2 electrons, so it's already got 12 electrons. But if I go back to our periodic table, right, sulfur's in the 3rd row of that periodic table, so more than 8 electrons for sulfur is fine. That's not a big deal. So sulfur does have those like empty d orbitals and really just that extra space to be able to hold those extra electrons. All right, so that would be our Lewis structure then. We don't need to do anything else for it. Everything has, oops, if I can spell here. And if we think of formal charge, which is always still a good idea to check at the end, all of our fluorines, they have 3 lone pairs in 1 bond, which for all of our halogens, that's kind of their usual conformation to have 0 formal charge. Sulfur has 6 valence electrons normally. It's made 6 bonds, has no lone pairs, also has a 0 formal charge. So that's it for our Lewis structure. Now, our geometries then, for our electron geometry, well, I mentioned this is the one that we haven't seen yet. So it's the one when we have 6 things around our central atom. We have 6 fluorines. And even though it sounds a little bit weird initially, if there's 6 things around our central atom, we actually refer to that as octahedral. For our molecular geometry on this molecule, we said a couple examples ago, anytime there's no lone pairs in the central atom, then your electron and molecular geometries are the same. And so that's what we'll see here. We have octahedral for our electron geometry here as well. All right. Now, the VSEPR sketch. This is kind of one of the reasons I really wanted to show this geometry. So to try and show this thing in 3 dimensions. Best way to do that, we have our central atom. Make kind of almost like a square arrangement going around it. And then we can have a wedge that's going, a wedge coming towards us, dash lines kind of going away, right? And that would be our kind of general orientation. Now we can add each of our fluorines, since everything is a fluorine here. And that would be our general VSEPR sketch. And kind of like I mentioned earlier, when I drew the original Lewis structure, like the VSEPR sketch for octahedral looks a lot like a 3-dimensional Cartesian coordinate system with an x, y, and z axis, right? It's all just perpendicular to each other. And so like really, these fluorines that I've drawn this way, they're really coming straight in and out of the page or the board that you're looking at. But we kind of draw them at this slight angle with the wedge and the dash, because on a 2D page, it's hard to draw that efficiently coming in and out of the board straight at us or away. All right, so I think that should hopefully be sufficient to kind of go through just a large number of examples in terms of seeing the different geometries, seeing some resonance, formal charge, some other factors like that tied in as well, and identifying things like the electron and molecular geometries and the Vesper sketch to go along with those Lewis structures. So I'm going to wrap things up here for this week's kind of demonstration. Next week, I'll do something very similar to this. I'll go through and kind of pick a few examples and go through kind of the same process for the things that we're going to look at next week with hybridization and types of bonds as far as like sigma and pi and something called like valence bond sketches or VB sketches. And so next week I'll kind of go through the same process in the demonstration video for those as well. So again, hopefully when you go to start working on the packets for these, you kind of understand what each of the pieces of things are really looking for or asking for. If anyone does have questions on things, this assignment is on CSE Pub, but what I suggest is print the questions printout, put all of your answers on basically what you print, and then what you're actually going to do is kind of either scan or take a picture of all of the work that you've put into that packet, and you're uploading that as one file. That's what you're actually submitting for this assignment on CSE Pub for next week. So kind of keep that in mind, especially if you're drawing kind of these Vesper sketches or Lewis structures. Maybe draw them on a separate sheet first so that you know what they're going to look like, and then put all that information in the packet that you plan to take pictures of and submit. And that hopefully will make it easier on your instructors when we go to kind of look through all of them to do any of the grading. But if anyone does have questions, feel free to email myself or any of your other instructors, and we'll be happy to help as much as we can. And we'll see you next time.